dear viewers, hope you will find today we will talk about the compartment modeling, which is related with your clinical pharmacy. So let's take a start about compartment modeling. Okay, this is the content. So look at the content. Compartment model has been classified into two categories. The first one is one compartment open model, and the second one is extravascular administrations. One compartment open model is in the form of IV bolus and IV infusions, while extravascular administrations. A compartment models is a group of tissue with similar blood flow and drug affinity. If we also know about all these things as we have discussed in our previous lectures, that how the blood is circulated throughout the body and different compartments. So a compartment is a physiologic and anatomic regions. Compartment is the traditional and most widely used approach to pharmacokinetic characterization of drug. These models simply interpolate the instrumental data and allow on empirical formula to estimate the drug concentration with time. How the drug concentrations in changes with time, which we have already discussed in our previous lectures. Now look at here the assumptions of the compartment models. According to the assumptions of compartment model, the body is represented as a series of compartments arranged in serials or parallel to each other. As we know that the rate of drug movement between the compartment is described by the first order kinetic. The rate constants, they are used to represent rate of entry into an exit from compartment. A statistical analysis of plasma concentration time data is another method used to find out a number of compartment models. Now look at here the various application of compartment modelings. What are the advantages of compartment modeling? So the first one is it is very simple and flexible approach and widely used. It gives a visual representation of various rate processes involved in drug dispositions, which is useful in predicting drug concentration time profile in both normal and pathological composition. So it is useful in relating the drug plasma level and therapeutic and toxic levels. So we can here an application of compartment model, we can correlate the pharmacology with clinical pharmacy. So how they can be correlated? So the first one which I am going to explain, that is one compartment models. So one compartment model, that is also called instantaneous distribution models. Now what is one compartment models? So one compartment model is the time course of drug concentration which is determined after the administration, can satisfactorily explained by assuming the body is a single well-mixed compartment with first order disposition process. Actually in one compartment models, the body is constituted as a single kinetically homogeneous unit with no barriers to the movement of drugs. And one compartment models the elimination as a first order process with first order rate constant. As we have discussed in first order kinetic, that the concentrations is historically proportional to the rate of reactions. Here the drugs move dynamically in and out of the compartment, then the rate of input will be greater than the rate of output. Okay, let's see here in one compartment open models. The term open mean that the input availability indicate the eliminations, and they are unidirectionals, which are said that the drug can be eliminated from the output be the body. This is also a very important classification of one compartment open model. So one compartment open models, depending upon the rate of input, several one compartment model they are defined. So in one compartment open models, there is intravenous bolus administrations, and one compartment open models you can say there is continuous intravenous infusions, and one compartment open model also involve extravascular zero order absorptions. One compartment open model extravascular first order absorption. So this is the classification of one compartment open models. Now let's see here. Let's suppose this is intravenous bolus administration, when a drug that distributes in body as given in the palm of a lipid intravenous injection, so it takes about 1 or 3 times for complete circulations. The model can be diagrammatically depicted as this is the blood, and the others you can say the blood and other body tissues, and this is elimination constant. That's how after administration of drug, at which rate the drug has been eliminated from the body. So now let's see here, it can be mathematically expressed or represented as, this is the general expression for the rate of drug penetration to the body, also how the drug is penetrated inside the body and what are the changes which are occurs. So that is mathematically it can be written as dx by dt is equal to this is rate in availability, the difference between rate in availability and rate out elimination. So it can represent the difference between rate in availability and rate out elimination dx by dt. Since the rate or absorptions is absent, when the rate in or absorption is absent, then the equation can be written as dx by dt is equal to minus mean decrease the rate out, because here in this case the rate is the rate in or absorption is absent. Now let's suppose if the rate out or elimination follow first order kinetic, then dx by dt is equal to minus kex. It means that the where, now let's see here, where the ke is the first order elimination rate constant, which we have already discussed, that the concentrations of the drug that is depends, greater will be the concentrations of the drug, so more and more drug will be eliminated from your body, and x is the this x is the amount of drug in the body at any time remaining to be eliminated, while the ke mean the first order elimination rate constant, so minus mean decrease the rate of eliminations. The negative sign indicates that the drug is being lost from the body. It means the drug is being eliminated from the body. The drug is being excreted from the body. The negative sign indicates like that. Okay, now let's come toward the estimation of pharmacokinetic profiles. Now we will discuss about the estimations, how we can estimate the pharmacokinetic parameters. So for a drug that follows the one compartment kinetic and administer as rapid IV injections, so the decline in the plasma drug concentration is only due to elimination of drug from the body and not due to distribution. So the phase being as elimination phase. The elimination phase can be characterized by the three parameters. So the first one is elimination rate constant, the second one is elimination half-life, and the third one is drug clearance. Let's see here, this is the graphical representation, concentration with time. The Cartesian plot of the drug that follow the one compartment kinetics and given by the rapid IV injections, and with the semi-logarithmic plot for the rate of eliminations and a one compartment model. So let's see here, as we have discussed about the half-life, that the time which is required for a drug to achieve the peak plasma concentration to be half of its original concentration. It means that let's suppose if a drug half-life is 2 hours, so it means that after 2 hours the original concentration of the drug will be reduced 50%. So this is the regular Cartesian plot. So this is T half 1/2, this is the half-life. So look at this graphical representation. So this is actually concentration of the drug. So the concentration of the drug is reduced with the passage of times. And this is log concentrations. It can be shown by logarithmically. So this is Cartesian plot of a drug that follow the one compartment kinetic and given by rapid IV injection. So look at here. So this is semi-logarithmic plot. So this is straight. Look at this line is straight. Log C2 and log C1. So mathematically semi-logarithmic plot, this is T1 and T2. So this is the difference. You can say this is the T1 and T2. T1/2, this is the half-life. But here the difference and these two graphical representation, this is log concentration and this is simple, that the concentration of the drug is reduced with the passage of time. But here the line is straight and here the line is curved. So this is regular Cartesian plot. So this show that the concentration of the drug is reduced with time. So it can be represented mathematically. The slope, this is a straight line. So look at here. So the slope is equal to minus k divided by 2.303, and this it become equal to log C1. Log, this is log C1. This is the first one, Cartesian. This is in simple words you can say one compartment kinetics given by rapid injections, semi-logarithmic plot for the rate of elimination of compartment models. So this is log C1 minus the difference between these two. It can be divided by 2.303 and T1 minus T2. Elimination half-life. Elimination half-life can be defined as defined as the time taken for the amount of drug in the body as well as the plasma concentration to decline by 1/2 or 50% its initial value. T1/2 mathematically it can be represented by T1/2 is equal to 0.693 divided by K, or half-life of drug that is equal to 0.693 multiplied by volume of distribution divided by drug clearance. So this is called elimination of half-life. Thank you so much for watching my lecture. Inshallah, in my next lectures I will discuss about the apparent volume of distribution. What is apparent volume of distribution? What is elimination half-life? Thank you so much for watching my lecture, dear students. Wish you all the best.